Hi to everybody. Thank you so much for coming here today. I would like also to thank the member of the committee for accepting to be part of my jury. I know this takes a bit of work, and I really appreciate what you are doing and what you did for me. Thank you so much. So today we're going to talk about corals. So corals are colonial organisms that live in symbiosis with tiny algae of the family Symbiodinaceae. These algae are able to produce autotrophic carbon through photosynthesis that can be used by the coral. Also, corals are able to feed, since there are animals, they are able to feed on other food sources, like in this photo of an acropora feeding on zooplankton. And this type of carbon can be defined as a heterotrophic carbon. In both cases, autotrophic and heterotrophic carbon can be used by the corals, convert in energy, and can be used by the coral to build the calcium carbonate skeleton, and also can be invested or allocated in some biological processes such as reproduction or survival and growth. So different species of corals can cohabit, and they can form what we know as a coral reef. Here there is a coral reef in Lifu, for example, here in New Caledonia. There are 10 different ecoregions worldwide where we can find coral reef, and coral reef are normally distributed between the tropical of Cancer and tropical of Capricorn. That's because their distribution is connected to a specific environmental condition, such as temperature, salinity, and in general, water quality. Unfortunately, corals are under threat, and that's because of climate change. So here there is a map with the same ecoregion where we can find coral reef. In this small plot on the side, there are just the coral cover, and we can see each ecoregion. So we can see how coral cover in each ecoregion is actually declining in the few years, and that's mostly because of the increase of temperature and effect of climate change. That's why researchers are actually focusing on coral that live at the age of the environmental limits. So here there is a picture reporting the number of studies evaluating the response of coral under extreme temperature or extreme pH. And we can see how these studies start to come up around the year 2000, so quite recently. Since time passed by, we have more definition on the, we define more, scientists define more what are extreme coral reef. Now we can define extreme coral reef as all those reefs that develop under extreme environmental conditions. Most of the study have been reported the response of corals in the CO2 vents of Papua New Guinea, or the corals, response of corals in macrotidal environments of Kimberley region in Australia. However, there are new study sites that are starting to emerge, and one of those is the semi-enclosed lagoon of Buraque in New Caledonia. The semi-enclosed lagoon of Buraque, it's located on the western side of Le Grande Terre in New Caledonia, therefore, and it's characterized by a channel that makes its way into a dense mangrove forest. Now, the interest of this study site, it's because the environmental condition or physicochemical parameters such as pH, dissolved oxygen, and temperature can fluctuate and are also connected with the tide, as we can see here. That's because high tide, new water comes inside the system and spread in the shallow part of the mangroves, where it gets deoxygenated, more acidic, and warmer in summer. Then at low tide, that water drains inside the system and exposes corals to different water with different physicochemical parameters. As a result of that, the 66 coral species that have been described in semi-enclosed lagoon of Buraque are normally exposed to variation in pH that can go from 7.2 to 8, variation of dissolved oxygen that can go from 2 to 7.2, and variation in temperature that can be up to 5 degrees, just in a few hours. So since 2016, when this study site was evaluated for the first time, few studies were published. So what we know about the corals in the semi-enclosed lagoon of Boracay right now, it's that they can have a variable metabolic response and variable calcification, then some dissimilarity in their algal salmon community and the microbial community have been found between the corals that live in Boracay and corals that live in the reference site. And a recent study actually observed high recruitment rates inside Boracay. However, these studies are really put the basis of what we know about this system and how corals can deal with stress, but they actually open new research gaps, such as it's not clear if the metabolic response of corals is species-specific or if it's more linked to seasonal variation. Indeed, most of the studies that have been done in the same period between December and March. Another another question that's still open, it's like not clear what are the traits or if there are any specific traits that can confer resistance to those corals. And despite the study that report high coral recruitment, it's not clear if extreme corals are actually able to reproduce or undergo through gametogenesis. Therefore, I developed my objective of this study, of this thesis. The first objective is more focused on the physiological traits, and I developed 3 different points for that objective. We know that when corals are exposed to stress, they can actually respond differently, and their response is due to the intensity, the frequency of the stress, and the capacity of the coral to respond to that specific stress. The capacity of the coral to tolerate that specific stress. So we know that when corals are exposed to different stress, they can develop and manifest different types of phenotypical responses. Sometimes these phenotypical responses are not enough to deal with that stress, but sometimes that phenotypical plasticity is actually conduce the coral to acclimatize. And that's my first point, where I wanted to define the coral climatization capacity of corals in Boracay. The second point, it's more based on the fact that individuals that have grown and exposed to a constant type of stress, and different individuals of the same population can actually report or manifest some traits more often. So some physiological traits that can become more frequent in that population. So that's what I wanted to do with the second point, where I wanted to evaluate and try to identify some traits associated with stress resistance with those corals. Then the third point, it's more based on the thing that phenotypical plasticity has some costs, some limits. So I wanted just to evaluate the temporal variation of biochemical compounds because they can be sources of energy for corals, and really nothing is known in literature. The second objective is more based on coral phenology. So we know that adaptation can be supported by reproductive success, and this comports that corals are able to undergo through gametogenesis and produce a high number of gametes and of high quality, and from survival or local recruits. To do so, I chose 4 different species. I chose those species because they are branching species. They are widely present in Boracay. They belong to the same family, but they are part of different genus. And there are previous studies of those species inside Boracay and control site. Now, I also chose those species because for the way they can acquire the algal salmon community. Indeed, horizontal transfer species, such as Acropora, for example, are able to, the early life stages of those type of corals, and especially recruits, are able to uptake the algal salmon community from the new environment they will settle, while vertical transfer species are actually able to transfer the algal salmon community to their offspring. So it's a completely different strategy. Therefore, we arrive to the first objective, which is to define acclimatization capacity of extreme corals in variable conditions. So for this objective, I chose 2 species, Montipora stellata and Acropora tenuis. I also select 2 different control sites, one inshore control site and one offshore control site, Pierre. I chose these two control sites because I assumed that the colony that came from those sites had different environmental history. Therefore, they were exposed to different types of stress in the past. Then I split those colonies in half, and I back transplant half of those colonies back in their origin site. Then I transplanted the other half of those colonies inside Bouraké. I did a bit the same with the colonies Bouraké in terms that I chose some colonies in Bouraké, I split them in half, and I back transplanted half colonies together with the other non-native colonies. Therefore, I created 5 different categories, which are colonies of Bouraké in Bouraké, the colonies of the inshore site are 2 in the inshore site, colony of the inshore site are 2 in Bouraké, and I did the same thing for the offshore colonies. So I put those colonies on a common garden. So there were 3 different common gardens in total, one at each site, origin site. Then I monitored survivorship for 11 months. And I took a bunch of samples in winter and summer because I wanted to define different physiological metrics. But today, I'm just going to present a few of them because I don't have time. So let's start with the survivorship. Here we have the percentage survival of the colonies over time across the different conditions. So we noticed the first sign of mortality around after 220 days, which was actually in February. We can see how Montipora stellata didn't show high mortality rates at the point, but the colonies from the offshore site that we transplanted inside Bouraké were actually in state of bleaching, and they all died after. Then if we look at the different species Acropora tenuis, we actually had completely different response. Indeed, all the colonies that we transplanted inside Bouraké from the reference site, they all died, while Bouraké colonies display more than 50% of survival rate. So as a first step, I look at the environmental condition just to understand what happened. Here you have the black line, it's the salinity, the red line is the temperature, and the purple line is actually the light. So as a first thing, I was kind of, not shocked, but I was kind of surprised that the salinity just before our survey dropped down to 12 PSU. And then when I look at temperature, just before this drop in salinity, I noticed that temperature was quite high, and just after the drop in salinity, temperatures start to spike to up to 32 degrees. And in all of this, the light was quite reduced. So which means that corals, the algae that live in symbiosis with corals must reduce the photosynthesis. So corals are forced to feed on other sources of food, or they are pushed to catabolize the energetical reserves to survive. Here there is the average growth rate of the colonies at their reference colonies at the origin site. So blue, it's the offshore colonies, and red will be the R2 inshore colonies, and the same colonies transplanted in Bouraké together with the black dots, which is represent the Bouraké colonies. So as a first result, we observed that Montipora stellata increased growth rates in the new environment, so in Bouraké, while Acropora tenuis did not change the growth rates. The second interesting result was the total carbohydrate. Indeed, Montipora stellata did not change their carbohydrates between the two environments, while Acropora tenuis decreased the carbohydrates content when was moved to Bouraké. Here there is the relative abundances of the ITS2 sequences. The ITS, for the people that are here, the ITS2 sequences are just, it's just a primer that we can use to sequence a part of the DNA of the plants and algae, and give us some information on the algal symbiont species that live in symbiosis with coral. So here we have the major sequences of offshore colonies in their origin site and the offshore colonies at their transplanted site. And we can see how they kept the same algal symbiont community. And here we can see the inshore colonies that did the same, but they had completely different algal symbiont community compared to the offshore colonies. So they kept their fidelity with their algal symbiont community. Then if we look at Buraké, they had high similarity with the inshore colonies, but the major sequences in Buraké were really different from the offshore colonies that we transplant inside Buraké and at the reference site. We did the same thing at the beginning of the transplanting in winter and summer, and we found exactly the same trend. Now here there is Acropora tenuis, which had exactly the same type of trend. It just looks a bit more confusing because normally Acropora species have more species that live in symbiosis with them, so more diversified community. Anyway, it's the same trend. So the reference corals kept the same major sequences when they were transplanted, and we observed similarity between the Buraké colonies and the inshore colonies. So to sum up these results, we observed different survival for the two species. We observed an increased growth for Montipora stellata and a catabolism of carbohydrates in Acropora tenuis. Then they had similar responses because they both increased their respiration, and both species from the inshore side had similar symbiodinase community compared to Buraké population. So these results are in preparation submission for Ecosphere. Now, we just saw how Acropora tenuis had less plasticity compared to Montipora stellata. But if we look at the literature, we know that Acropora tenuis, together with other Acroporas, represent more than 95% of the corals in the most extreme site of Buraké Beach. So here comes my question and my interest in investigating the traits associated with stress resistance in a long life adapted coral of Buraké. So for this objective, I chose Acropora muricata because there was a previous study on this species for the same site. So then I selected B2 as a site and and a nearby control site R1. For this experience, we basically took advantages from a bleaching event that happened in Buraké, but not outside, which was quite interesting. So we tagged some unbleached colony inside Buraké, and then we tagged some unbleached colonies in the near control site. Then I created 3 different categories: Buraké bleach, Buraké with zooxanthellae, and reference with zooxanthellae. Then I select those colony at the moment of the bleaching, and I tag them. And then I resample those colony again after 4 months in May. In this case, I wanted to define different physiological metrics, but today I'm gonna just talk about a couple of them. So let's start with survivorship. We observed just 20% of survivorship in the bleached colonies of Buraké, as expected. Then we observed 80% of survival rates in the bleached colony of Buraké, and we could only find 66% of the colonies at the reference site. Then again, I look at the environmental parameters. So when I look at temperature and I realized that there was this huge drop in temperature, I realized that probably this bleaching event was induced by the combination of drop in salinity and temperature, because we know that 2021 was the first year of La Niña New Caledonia, which is normally associated with intense period of rain. And we start to observe the rainy season the beginning of January, and we observed the bleaching just in the middle of January. Then we had a tropical storm Lucas and a cyclone Niran passing by our control site, which probably can explain the thing that we lost some of the reference colonies and also some mortality in unbleached Buraké colonies. So here I decide to report the simian count for surface during bleaching and after bleaching for the 3 categories. just because I wanted to stress that the bleach colony, actually recovered completely at the post-bleaching because they had similar number of symbiont per surface compared to the reference sites. Then the second metric is actually total carbohydrate again, because I noticed something interesting, such as the Burake colonies had higher concentration carbohydrates compared to the reference colonies, and that was more evident after bleaching. Here we are again with the relative abundances of ITS2 sequences. So we can notice how the bleached colonies had different major sequences compared to the unbleached colony at the moment of the bleaching. The second result is that control had higher diversity. I mean, each individual, the control was more diversified. They had different type of symbiont community compared to Burake population, where each individual for each category had exactly the same type of relative abundances. Here there are the data after bleaching, and we can see how the 3 bleached colonies that survive uptake the same major sequences of the unbleached colony just after recovery. And then the control, the reference colony actually kept the differences between the reference site and Burake population. So to sum up the results, we observed that bleached colony changes the ITS2 major sequence between bleaching and post-bleaching, and we observed that colonies from the reference site had different algal symbiont community compared to Burake population. So this, the results of this study have been published, will be available online soon on PLOS ONE. So we just saw how biochemical compounds can have, are quite interesting in Burake corals because we observe high quantity of carbohydrates. Now, I was just interested in see how the other energetical reservoirs will be and will vary in time, because lipids are actually one of the components that's most represented in gametogenesis. So here come my next objective, which was to explore temporal variation in biochemical compounds of extreme corals. For this point, I use the same experimental design that I presented in the first objective. So there are the same species, and there are the same site, inshore R2, Burake, and the offshore PR, and my AF colonies that were places in the common garden. But this time, I sampled those colonies every 3 months, and I increased the frequency of the sampling between October and December. Then I did a bunch of biochemical analysis, and today I'm just going to talk about the lipids because they represent the link with the reproduction. So here there is the variation of total lipids in time for Montipora stellata, Acropora tenuis, from Burake corals in black, R2 inshore colonies in red, and offshore colonies in blue. So we had different results. The first one is that we can observe as Montipora stellata had higher lipid content compared to Acropora tenuis. The second result was quite interesting, was a drop in lipid between November and December. It was present in both species, more evident in Montipora. And then the other results was that actually Acropora tenuis catabolized a lot of lipids in February when there was a really intense period of stress. So this study produced a lot of results, but today I just want you to focus on 3 main take-home messages, which is we observe a substantial decrease in lipid between November and December. We observed that Acropora tenuis had more carbohydrates and more protein, but actually Montipora stellata had more lipids. So these results have been written in a scientific note, and they are still a bit in preparation. So now that we saw that there was a variation in lipids between November and December, I actually wanted to investigate it and dig in a bit more on the gametogenesis. Because lipids are, as I said before, are really one of the most component in oocyte formation. So here comes my other objective, which is to define the effect of stream and a high variable environment on gametogenesis. For this objective, I chose 3 different species: Montipora stellata, Montipora digitata, and Acropora tenuis. Then I had my Buraké site in comparison with different reference sites. So we had an inshore site R2 or R1 based on species presence. Then we had an offshore site in the south RS2 and an inshore site in the south RS2. Sorry, the other one was RS1. So I tagged my colonies and I sampled them approximately 10 days before the full moon of October and November and December in 2020 and 2021. Then I collected 2 branches for each colony and I decalcified them. Then I dissected 10 polyps for each branch, and I count the number of sites and define different metrics of fecundity. But today I just going to present a few results. So here there is the proportion of colonies that were estimated to spawn across all the sites in October 2021 and November 2021. What we observe here is the Acropora tenuis. The majority of the colonies from Buraké and the nearby control site actually were estimated to spawn in October, while the rest of the colony, together with the southern site, were estimated to spawn in November. Then for Montipora digitata, I observed the majority of the colonies again in Buraké and the nearby control site were estimated to spawn in November, and just some of them in the south spawned in November, and the rest were estimated to spawn in December. And here, Montipora stellata, we actually observe kind of same trend, where part of the colonies from Buraké and the nearby control site were estimated to spawn in October, and the rest of the colony were estimated to spawn in November, together with part of the colonies from the southern side. As a first step, I look at the temperature because I know that oocyte maturation is really related with the rise in temperature. And then I observed that starting from mid of September, the difference in average seawater temperature from the northern side, among which there is Buraké, and the southern side start to increase. So that kind of divergence trend probably could explain why we observe spawning asynchrony between northern and southern sites. Here there is the number of oocytes per fecund polyps, and we can see how we observe a moderately high number of oocytes per fecund polyps in Buraké, and actually in Acropora tenuis, this number of oocytes was significantly higher in Buraké compared to the other control sites. Looking at the oocyte sites, we observed that Acropora tenuis and Montipora digitata actually had smaller oocytes compared to the reference sites, while Montipora stellata did not report any differences across sites. So the results of these points, therefore, are that we didn't find any effect of the high environmental variability on the spawning timing, a spawning window, but we observe an asynchrony between northern and southern sites. We didn't detect any visible effect on polyp level colony level fecundity. However, we observed the oocyte of Acropora tenuis and Montipora digitata were smaller in Buraké. So these results have been written on the formal scientific article and will be submitted in Coral Reef soon. They were supposed to be submitted in December, but they will be submitted soon. So we just saw how corals in Buraké are actually able to undergo through gametogenesis. But we know that genetic diversity relies also in recruitment success. Therefore, here comes my other objective, which was investigate the effect of extreme and high variable environment on coral recruitment. For this objective, I used the same site of the I just presented with the coral gametogenesis before. So there is my Buraké site and the reference sites, but this time I put some recruitment tiles, terracotta recruitment tiles in 2020, 2021, and 2022. So I positioned the recruitment tiles 4 weeks before the full moon of October in 2020 in each year. I retrieved those tiles in February, and I actually bleached those tiles to identify and count the recruits on the surface. So here are the results of number of individuals per tiles across sites in each year. And we can see how in Buraque we actually observe a negatively, really low, a significantly lower recruitment rates compared to the other sites. And we also did not observe any temporal variation in recruitment over time, while in the other sites we actually observed some temporal variation. These results are a bit contradicting with the results of Tambet et al. 2022. We actually reported high recruitment inside Buraque. However, currently with Tambet et al., we observed that Acroporidae was the major represented family in all sites, except for R2, where actually Poeciloporidae was the major family represented. So I was a bit curious to understand why we observed different results of Tambet et al. So I started making different hypotheses. And I hypothesized that maybe there were some part of the lagoons that were probably there could be a high level of larval retention and algal survivorship. So I put the recruitment tiles at different sites inside the semi-enclosed lagoon of Buraque, because I thought that maybe the high current that we have in the channel could have actually impacted the local recruitment, while in this enclave in B3, we probably could have higher recruitment. So I just tested this hypothesis to start. And I observed that there was no changes in coral recruitment across the semi-enclosed lagoon of Buraque. So the main results are that I didn't observe any temporal variation in coral recruitment in Buraque, where actually recruitment was negatively affected. Acroporidae was the major family represented, and I didn't observe any change across the semi-enclosed lagoon of Buraque in 2022. So here we come to the main question of one of the main questions of my thesis, which is define how coral are able to acclimatize and survive under the extreme condition of Buraque. So we observed that the two species, Montipora stellata and Acropora tenuis, actually respond completely differently. So now the question is why? If we step back and we look at the difference between species, looking at the data of biochemical compounds, so data that comes from the colonies at their origin site, we can see how Montipora stellata actually has more biomass and lipid and tend to have more calcification compared to Acropora tenuis, which actually had more carbohydrates and more proteins. So these results suggest that these two species might have a different completely metabolism. Indeed, maybe Acropora tenuis can rely on carbohydrates that are produced during photosynthesis and can catabolize those carbohydrates to produce ATP and make their metabolism to run, while Montipora stellata can rely on other type of strategies to actually build up their energetical resources in the form of lipids and maybe use them under period of stress. If we look at the results of the colony that we transplanted inside Buraque, we actually kind of can confirm this hypothesis because we observe increased growth in Montipora stellata in Buraque, and we also observe catabolism of carbohydrates in Montipora stellata. And both species had higher respiration, which can suggest fast metabolism from one side. It can also suggest nutritional plasticity for Montipora stellata, which can be, again, a strategy in stressful environments. But maybe this strategy is not enough when there is an acute event of stress. Indeed, the Buraque, the offshore colonies of Montipora that we transplanted inside Buraque actually bleached and died. So this suggests that there might be another process that can change this type of the type of response of corals in Burake. It's not just a species difference, but there is something else.
Buonasera, come posso aiutarti?
Sorry. Okay. That was Siri. I don't know why Siri started. Sorry. So now the question is how, what else could have promoted acclimatization of Earth to inshore colonies in Burake? So sorry, we lost the focus, but that's the question. So the other difference that we observed between the offshore colonies and the inshore colonies that we transplanted in Burake was also in their algal symbiont community. Indeed, the offshore colonies had completely different major sequence compared to the inshore colonies, which actually resulted very similar to the Burake colonies. However, this can suggest that maybe the symbiont can give the difference in survivorship rate, but we need to be careful with that because actually also Acropora tenuis from Burake had similar major sequence compared to the inshore colonies that were transplanted in Burake. But those inshore colonies died. So this type of results actually suggest me that maybe there are other type of mechanisms that could explain the different survivorship between these two species. And maybe I'm assuming that the way the Montipora and Acropora species can acquire the algal symbiont community could make the difference. Indeed, we know that Acropora corals can produce their gametes, they release their gametes, they undergo through embryogenesis and planulation, then they will settle in a new environment and they will uptake locally adapted algal symbiont community from the new environment. While Montipora species are able to pass their algal symbiont community to their offspring, so the new recruits will already have an existing algal symbiont community. So the question I posed to myself was how Montipora species can actually acquire resistance over time if they pass always the same algal symbiont community to their offspring. Well, the answer came from an article of Quigley et al. 2019 that actually said that also vertical species can shuffle the algal symbiont community, and that's the way this type of species increase their resistance to stress. And they are able to pass the shuffle community to their offspring as well. So if we move on and we look at the spawning data, or spawning window, we can see how Burake colonies had a synchronized spawning with the nearby control site. And we know that synchronized spawning can actually increase the connectivity between different sites. So that pushed me to make the hypothesis that maybe we don't have just Burake population, that maybe Burake population is not really isolated, but it's connected with a close by near site, and that's probably why Montipora stellata from the inshore colonies could have survived inside Burake. Going on with the results of fecundity, we observed that also the oocyte from the Montipora digitata and Acropora tenuis were smaller. So we know that the smaller oocyte can actually produce or reduce the reproductive success of corals, which is actually what we observe in Burake, because we had a really low recruitment. If larva retention is high, if the larvae have higher survivorship rate. Indeed, we didn't test this hypothesis, so we can't conclude on this part of my thesis, because indeed there could be different variables that could have affect the recruitment at that point. Indeed, it could have been that the recruitment tiles did not have enough attractive settlement cues, so maybe the recruitment was low for that reason, or maybe we had high recruitment actually in Burake, but the La Niña 2021 and 2022 caused a big mortality, and we could not count those recruits because they were dissolved by the low pH. So to conclude, with my thesis, I understood that acclimatization capacity can be species-specific and based on coral environmental history. I also understood that coral stress resistance can be promoted by symbiosis with symbiodinase that acquired stress tolerance. The coral gametogenesis in extreme corals can actually, it's possible, but there are some trade-offs. And the environmental pressure can actually reduce early life history stages, possibly creating some bottleneck at population level. Now, as I try to respond to some research question, of course, other research question open. So in my opinion, the next steps, the next research should focus on the effect on the environment, on fertilization, larval physiology, and settlement, just to test if these stages are affected by the environment from the Buraki population. Then I think that stress tolerance should be tested in early life history stages. Indeed, it would be nice to test if the adult colonies in Buraki can actually pass stress tolerance to their offspring and to their juvenile stages. So if stress tolerance is actually heritable. And of course, test if there is a connectivity among population, because we noticed that the nearby, if this is the case, the nearby reference site could have also, the colony-induced site could have also some traits that can increase fitness under climate change. Thank you so much, everyone.
Thank you, Cinzia. Good timing. So now it's time for discussion with a member of the jury. Can you start, Christine?
Yes. So thanks a lot, first, Cinzia, for this very nice presentation of your results. Well, I would like to thank also Ricardo, Claude, Hugues, to have invited me to be part of this committee, and also Cinzia. It's a very nice thesis. Cinzia and the supervisors who have dived with you, and but it's a very nice thesis. I really appreciate it. It was a lot of work, a lot of diving. So it was not obvious at the beginning to, when you start the thesis, I think, to achieve such an amazing work. So really, congratulations. My first comment is just a comment for the introduction chapter that I found a bit short compared to all the results you've got. And maybe I would have liked to see a chapter on the different processes, strategies of acclimatization and adaptation of corals, and which one you consider among all these processes. Well, this is just a small comment, it's more, but it would have been easier maybe for the rest of the thesis. And also the research gaps and the objectives of each chapter, it would have been good to have summarized in the introduction. Well, this is just a small comment, I would say. Not really a criticism. It's just, I know that the end of the thesis are always hard, and you don't have always the time to expand the introductions, so it's not a problem. You partly answered to one of my questions about the recruitment. You said that your results were different from the one of Tanvet, that Tanvet found a high recruitment in Buraki, and in your study you found that the recruitment was not so important. And my question was that you put the tiles in Buraki just a few weeks before the recruitment, and maybe the tiles could not have been colonized by the right microbiome or something like this. And also you look at the recruitment during El Nino, I don't know, in a very hot year. So what would you expect it, were the different setup, well, if you would have done this experiment in a normal year, I would say, not very hot, and if you would have put the tiles more in advance, or if you return now in Bourraquet and you look at your tiles, what would you expect?
Yeah, thank you so much for the question, and thank you so much for the comments on the introduction. I think I have 3 months of time before submitting my manuscript, so I can actually add that part, that your comments at the introduction. So it will be, I think it's a good suggestion.
It was just a comment. It's not that we want you to change your thesis.
Okay, thanks. I think it's a good comment though. Then for recruitment here, there is the results of Tambet et al. On the right and my results on the left. So yeah, there was a different number of recruits, but well, what would I do? Well, first of all, I would like to give my explanation why maybe that we observed those differences. So the setting between Tambet et al. Was a bit different from my setting. Indeed, Tambet et al. Input some tiles with already existing CA, so crustose coralline algae, on the tiles, which are really attractive for crowpora larvae. So while in my case, I just put the tiles and I wait for the for the biofilm to grow naturally on each site, reference site. So that's why I thought that maybe the settlement was different, our results were different. But if I could go back in time, probably I think you did a really, good comment. Maybe 4 weeks was not enough for the biofilm to build on those tiles. So maybe I could, if I could go back in time, I will put them maybe 2 months before or maybe even more. But the thing is that actually when I start write this type of question was when we already did the first year of data collection. So I decided to keep going with our method afterwards, just to use the same type of setting across the years and not create some variability, some noise in our results. And yes, we had La Niña, which, was in 2021. I personally was not expecting La Niña again in 2022. That's why I settled the long-term experiment in that year. But actually, sometimes even if you plan things in advance, they take another direction, and that's totally fine. It's okay. But yeah, probably I will try to do different type of timing, like preconditioning timing, to see if can change, the recruitment could change.
Okay. And do you think it would be interesting to analyze or the CCA or the microbiome on the tiles also?
Yeah, I think it will be that will be another research question, which will be how the environmental condition can affect colonization over time, which is really interesting question. I'm assuming that the type of colonization will be different just because I retrieved the tiles in February, at the end of February. So there was quite a few months, and I still could detect a difference, like visual difference between the community, between a reference site and Bourraquet, for example. So I think they could produce nice results.
Okay. And for the spawning patterns, you said that more studies are needed to explain the complexity of the spawning patterns among coral populations in New Caledonia. And what would you do or suggest doing in the future to investigate this?
Yeah, thank you for the question, because I really care about this chapter. If I could do something, I will definitely do a sampling for all year round. Like tag some colonies, probably increase the number of colonies tagged, and follow them all year round, and not just focusing on the spawning period. But that's a lot of work, especially because with my method, I dissected the polyps, and it takes a lot of time. I take the measure. So in my case, for my thesis, was not really possible to focus on that, but I actually think it was okay to just do what I did, like focusing on the spawning period. But it will definitely be interesting to have a long series of data across the year. And with different species, I actually think that would be also nice to collect some samples from the south of New Caledonia to the north of New Caledonia, just to see if there is really an asynchrony in the spawning. And because, again, there is really nothing on gametogenesis of corals in New Caledonia, which is one of the biggest reefs in the world. And it's, I think it's really interesting. It should be done. Thanks.
Good. Okay, so for the chapter, I don't remember, 4.2, where you investigate the carbohydrates, lipids, proteins, or whatever in the 2 coral species. Well, this chapter in the thesis is a bit, it needs a bit of rewriting, especially for the material and methods and for the figures that were not so clear. But what I kept is, and you said in your conclusion, that Acropora has more carbohydrates than Montipora, that has more lipids. And you said that Acropora has also died or resisted less to the stress than Montipora, right? But I think that can be explained because during stress, if Acropora needs to respire the carbohydrates, this will give less ATP, less energy than respiring lipids. So I think that it's an energetic, well, maybe it resists less to the stress because it has to respire carbohydrates instead of lipids. And lipids are more energetic. They can give more ATP than carbohydrates. And carbohydrates often lead to anoxic, the anoxic respiration that gives also lactate and all these byproducts. And it's maybe why Acropora resisted less to the stress than Montipora.
What? Sorry.
No, go. Sorry.
Yes, so I think that's why Acropora resisted less, because so what I observed also in Acropora muricata, there were more carbohydrates inside the buraque compared to outside. So I'm guessing that they really rely a lot on the carbohydrates that are produced through photosynthesis. And here we can see in this graph, for example, we can see how so the mechanisms, the basis, they rely more on carbohydrates. So if there is a really acute event of stress, they won't have a lot of lipids to catabolize. So they won't have enough energy to survive because, as you said exactly, lipids can actually release higher quantity of ATP compared to carbohydrates. But in that case, for example, in this moment, if we remember the variation of the environmental parameters, there was really low light at that time. So that means that probably the quantity of carbohydrates were reduced and they start to use lipids. But they don't have a lot of lipids in their tissue. So probably that's why they died. So yeah, probably mechanisms that could help those species in building up more lipids will be nutritional plasticity or external feeding. That could increase that, but I really notice a big difference between the 2 species, really. I don't know if I reply to your question.
If Montipora is more heterotroph than Acropora?
Okay, so yeah, there are a few studies in literature. There was Grottoli of 2006 who report that, where actually they observed that Montipora was more heterotrophic. So when under bleaching, they observed an increase in heterotrophy, and also been reported in the literature for this nutritional plasticity. And actually, this explains how this colony increased growth rates in buraque when they were transplanted in buraque. because we know that in Burake there is the mangroves, so there is a lot of organic matter, and they might have used some part of that organic matter to synthesize lipids or other biochemical compound.
Okay, great. Maybe my last question, I don't know, concerning the first chapter, went back to from the end to the beginning. You said that the acclimatization depends on the past thermal history of the corals. And then you showed also that, in fact, the corals which have resisted or to Burake conditions, they shift also their Symbiodiniaceae population they adapted their Symbiodiniaceae population. So for you, what is the most important, the past history or the Symbiodiniaceae?
That's a good question. That's a good question. I think they are both important. No, but I think that actually in species like vertical transfer species, for example, you can get with the environmental history. So if colonies are exposed to different stress, they can get more memory about the stress, and they can increase their tolerance. And that will be for the corals, but also will be for the symbiont that live in those corals. So yes, I can't respond completely to that question because it's difficult to really respond because yeah, I know that with Burake corals, for example, the algal symbiont community can increase the stress tolerance, but since we didn't do really adaptation, it's not possible to say how much the individual can actually apport to stress resistance.
Okay, and a bit my same question, if you were not in this particular year of El Niño event, would you have expected other results or corals to survive in Burake or?
That's a really good question. I was really upset when I found out that we got La Niña in 2022 because I was not expecting that. So I don't know what I will have assist. I mean, at the end, it's fine because we actually touch the stress limits of Burake population as well. So we noticed that also Burake population went to stress, which is type of information we couldn't get before. But yeah, I think Montipora would have resisted better than Acropora tennis overall. But I don't know about Acropora tennis because if we look at literature, Acropora is really represented in internal part of the semi-enclosed lagoon of Burake. So that means that those species can thrive in that environment somehow. It's still not clear if those individuals come from outside or if there is a high level retention, survivorship, and high selection of the environments. This is not clear. But yeah, Acropora can anyway survive under those environments. So I don't know really, sorry.
Oh, no, it's not a problem. Okay, so thank you, Cinzia. I will let the other reviewers to ask their questions. It's quite late for you. Thank you.
Thank you so much.
Thank you, Christine. Sylvain, it's up to you.
Yeah, thank you. Thank you. First, thank you for inviting me to be in the committee. It's great. It was great to read the thesis also, very instructive. And yes, congratulations. There's a lot of work in this thesis, which is quite impressive. Lots of experiment, big transplantation experiment, which is always very, very hard, and some monitoring on spawning also, which is quite hard. So regarding question, actually, the last question by Christine and your answer, like it's perfect link. First, I would like to say, like, think the fact that La Nina affected your corals is actually a chance. You know, you can turn it in a chance, and you did the good job of making the best of it and testing the resistance of the corals to their extreme. Now, I have questions because, like, you highlighted it also that in Burake, the dominant are Acropora, but in your results, the Acroporids, like, were the one that died the most. right, compared to multipolar. How can you explain that? Because you didn't really touch it. And maybe in my thinking is like the La Nina is quite exceptional. So when you talk about acclimatization, because they have been lifetime exposed to this extreme environment of Boracay, is it relevant in a La Nina period?
So thank you so much for your question. As a first thing, I would like to thank you as well for all the comments you did. You did a big job in going through all my manuscripts and leaving comments in the Word version of the manuscript. So thank you so much. I will address all those comments in the next 3 months. So yes, you made a really good point, saying that actually Acropora is really represented inside the semi-enclosed lagoon of Boracay. But in my experiment, I actually observed high mortality in Acropora. And I also asked that question to myself, because I was like, how come? So what I can say and what I realized is that actually, so these corals went through a big stress in 2021. So for our data, we observed that La Nina was the first year La Nina was in 2021, which, as you said, it's a periodic stress, so happens every few years. We observed that there was a bleaching event inside the semi-enclosed lagoon, and the Acropora were the most affected species, while Montipora did not. Was not just 1% of the Montiporas that we observe in our transit were actually affected by bleaching. So there was already a response there. Then what I think happened is actually these corals had a huge stress 1 year after the other. When normally this coral, normally La Nina it's just for 1 year, while this time we had 2 years La Nina in a row. So they had a back-to-back stress where like salinity really dropped to 12, which was crazy. And still 50% of the colonies that we tagged survived, which was impressive. So they do have high resistance, but I think they leave a bit of the age of the environmental limits. So they were already exposed to one stress before, and then they didn't have time really to recover fully. And then they were exposed to another stress. And I think most of the Acropora couldn't make it for that reason. Now, so if you look at Boracay right now, after these 2 years, the composition of the coral is changing a bit. So Montipora is taking over. So there are actually new species that start to spread inside the semi-enclosed lagoon of Boracay, which is still a Montipora that was not really observed before. So yeah, I think the Acropora corals have some resistance, but the stress, as I said before, environmental history, it actually depends as well on the intensity and frequency of the stress. They're already exposed to frequent stress, like in constant way. There was a kind of acute stress 1 year, then repeat the same year, the same stress after was maybe too much. That's my...
Yeah, and so the second, like for me, is you group every stress together, but here very much we are talking about the osmotic stress and even low temperature stress. But the Boracay acclimatization is rather like high temperature, low pH, and deoxygenation that happen on the tidal cycle. So like when talking about resistance, shall we focus the resistance to osmotic stress? It may be different mechanisms than resistance to high temperature. Can you discuss this point a little bit?
Sorry?
Can you discuss, like, because even I'm not really sure, what the resistance physiological mechanism or what physiological traits will provide osmotic resistance. Maybe the zooxanthellae clades, they're good against like high temperature, but they're not very good against osmotic stress. You know what I mean?
Yeah, I know what you mean, because yes, it's I thought about that as well. Which is osmotic stress is really a different type of stress compared to the others. But these corals, yes, were exposed to a constant type of stress plus osmotic stress. And I thought that maybe, we capture this decrease in salinity this time, but would tell us that maybe they were not exposed to this type of stress before, for example, Like not maybe drop in salinity like we observed this time, but kind of variation in salinity. So maybe as for the other factor, they develop some traits that actually can help them to deal with osmotic or decrease in salinity, which I thought maybe, I'm not sure about that, but maybe they could increase the quantity of mucus to isolate their tissue from the surrounding environments. For example, there could be a type of strategy they could have done. Or maybe, then I run out of ideas, but that production of mucus, I think, will be probably something that could help corals. Also during low tide, for example, for some corals that are exposed compared to others. I think that could be one of their strategy.
Yeah, I think it's quite interesting, you know, to have multi-stressors, and then you add another stressors on the top, and you see that actually the different species respond differently. And I agree that, like, at the end of the day, when they're bleached, they still need to feed on something, you know? So, like, I think the first is to not bleach resistance rather than resilience. But and your Montepora were very resilient in the meaning that they bleached and they recovered, which is maybe the advantage over the acropora that maybe they couldn't recover, you know, after the osmotic stress. I don't know. But I think there's something here to discuss on the mechanism of resistance and resilience against different types of stress. I have another question. Sorry, it's mostly on the first chapters, but actually also with spawning. Very interesting actually in the inshore reef sites. Because when you show the temperature in the inshore reef, in the spawning one, like the long-term temperature record, it actually worked very well with the Burake reef temperature.
Wait, I will take the graph. There. You talk about this graph, yeah?
Yeah.
Okay.
So if I'm correct, R2 is the inshore reef, right?
The northern inshore reef or the southern inshore reef?
R2 is which one? Sorry.
R2, it's a northern inshore reef.
So it's the same as in chapter 2 and so on, right?
So we did the analysis on temperature, average temperature, minimum temperature, maximum temperature of the site, and we observed that the close reference site had similarity in high temperature and low temperature and average temperature, if I'm not wrong. While Burake differ in high temperature and low temperature and also in average temperature from the rest. So the R2 site specifically, and that's why this paper is not still submitted in Coral Reef, it's just because we suspect, like this graph is the updated graph, but in the graph that you have in my manuscript that I sent you, there was a rise that was really weird in R2 compared to Burake and the other nearby site. And we suspected that actually the oboe started to drift or something happened. So we removed that data set, that part of the data set, since we started the oboe, so it was at the beginning of July. After, we suspect there was something really weird because the data were not coherent with what we observed before. So we removed this data. So it's difficult to talk about R2. But about R1, there are actually, the average temperature is similar to Burake. But if we look at the minimum temperature and maximum temperature, then that's when we got the difference, because in Burake we have high variability compared to R1 and R2 side.
So in special, but you touch a little bit at the end, you say that the population genetics would be interesting, and I completely agree. Like, because so R1 is the one that is close to Burake, or is sorry, I'm slightly lost now in the site. So is Burake R1 or R2? Is it the one in the chapter 2 that you call initial reef? Is which one?
Wait, I'm gonna find a map. Better map. Maybe this one.
Yeah, okay, okay, it's R2.
So R2, it's more close to Buraké. It's kind of a semi-enclosed reef. It's more
Okay.
open compared to Buraké, but no. And the R1 site is actually on the other side of the island. So it's actually closed.
It's
So
also like quite
yeah, they are in the same area, basically. One is on the internal part of the island, and the other one is on the southern part of the island.
Okay, so it's a very nice system, I feel, because like you have the Buraket, which is extremely variable, and then you have less variability in R1, R2, but still quite extreme average. And then you have your super control, I would say, which is flat and normal. And this is one point I feel like in the thesis, like we didn't talk much about variability, the importance of variability in acquisition of resistance. You know, like a sustained chronic extreme environment versus a highly variable. And I wonder, like, because Burake corals, they are every day exposed to massive variation. And there are some papers that suggest that this variability, extreme variability, is actually the one that bring most resistance compared to a chronic exposure to like harsh environment, you know. And I think here you have something to discuss because you have similar average but different variations. And this you didn't really discuss the importance of variability, which would have been nice. You have something to add on this?
Well, yes, that actually Buraké R2 and R1, they are kind of in a gradient. So as you said, there are differences in variability in Buraké and actually less variability in R2. That's why we choose this inshore site and transplant the colony of that inshore site inside. And then, in the literature is actually reported that environmental variability can increase the phenotypical plasticity of corals because the principle is that they are exposed to really extreme condition, but then they are balanced back, they go back to their kind of normal condition, so they can recover, and then again to extreme recover. So they can actually, with environmental memory, they can actually learn when the stress will come because it's really constant over time. So they can anticipate this type of stress. They can acquire this type of capacity over time. So it's true that R2 site is actually similar in the average value, but not in the variability. But when we transplant some of our colonies, like Montipora survived, which was really interesting because they didn't show any default in their physiological metrics at the moment where there was high stress, while Acropora actually didn't make it at all. So it's, there is probably something, some corals maybe can acquire some resistance as well, but the thing is that, exposed to variable environment probably gives them the capacity to a higher plasticity compared to the other colonies. Now, this is a bit tricky because that's why maybe I didn't comment that much, because when we did the transplant, we transplant the colonies from outside, inside Buraké, but we didn't transplant the Buraké colonies outside because it was unfeasible. It was too big and it was unfeasible. So I don't really have the response of Buraké colonies outside of the system. So I don't know if they have high plasticity in their system because they are completely adapted to that system and prepared to what's going to happen, or if they actually acquire that type of plasticity, they will function super well in another reef. I don't have that type of response, so that's why I didn't comment on that much, because I kind of have half of the information, if I reply to your question.
Yeah, I think it's quite a interesting system that you have there. Sorry, to be my last one, going to the comparison of recruitment with Stanved et al. And Christine also pointed out, but I have a just short specific question. Like in your experiment and in Stanved's experiment, which one had the more realistic CCA coverage for Burake?
Sorry, again, I couldn't understand.
Which experiment had the more realistic CCA coverage on the type for Burake? Because we know that Burake has low CCA, right?
Yes, exactly. But Tamvet is a friend of mine. I don't want to. No, I'm joking. Yeah, I see what you mean completely, and it's not to discredit the work of others because I really appreciate the work of other people are doing. But I think it's not really realistic when we bring it to Burake because, I mean, that's not the natural benthic community you can have on substrate. Because you are actually inserting a lot of CCA that we know from literature has a positive effect on settlement. So I will say that, yeah.
But it's actually very cool, I think. I think it's cool because you have one that you provide the cues, the chemical cues from the CCA, one you don't provide the cues, and then you can discuss what is the recruitment bottleneck. Is it the planula actually finding a stable substrate, or is it the post-settlement survival? Because normally they show that post-settlement survival can be high, and you show that maybe the Q are missing. So when you combine the two species, it's actually super interesting.
Yeah, it's really interesting. Indeed, it's still a question that's open. So my main supervisor actually is going further with this type of question. And as I know, recently he put some tiles with CCA and some tiles without CCA to see if there is a difference between the settlement in these two conditions. So we can have, I mean, my first question was to see if there was a difference in the across the semi-enclosed lagoon of Burake, and the answer is no. Now, with these tiles with different conditioning, we can see if the CCA has an effect or not, and then we can further proceed with trying to understand what are the main mechanisms, because, yeah, as I said, there are many factors that could they are involved in that in recruitment stages, phases.
I agree, but I like that two studies, they don't show the same, but because like there's some difference and it's important to consider. I mean, it's not one is bad, one is good. It's just it's a science, Okay,
Yes.
stop for me. Thank you very much.
Thank you, Sylvain.
Thank you, Sylvain. Emma, you can start.
Thank you. And Cinzia, great job. And it was a pleasure to read your thesis. And as we've heard from Christine and Sylvain, it was a huge amount of work. So yeah, you should be really proud. Each chapter I got to, I thought, well, this is a lot. And then there was another chapter and another one. So yeah, congratulations on that. Also, a couple of my big questions have just been answered. So Sylvain, thank you for that. The settlement Q1 was one of interest, and I think definitely something for further follow-up. So but I do have a few other questions that I wanted to ask you. And one kind of, I guess, really general one to start from your first chapter is, like, how are the reefs managed in New Caledonia? Like you mentioned that it's a UNESCO site, but like how in Australia we've got the Marine Park Authority, and I'm just interested to know, how the reefs and things are managed there.
Yes, thank you so much. You want to know how the reef in general in New Caledonia is going? Is that the question?
So in New Caledonia, is there like a government agency or like someone that gives you permits? Like how is the system like protected or managed?
Okay, yes, now I see the question. So yes, we need to ask some permission to collect samples. But since I also work in Australia, I can tell you that's not the same thing of Australia. So it's more free as soon as you inform and you report your results the local government, and you take them, you keep them updated on what you're doing. You're kind of transparent with them. They're really understanding and they are supportive as well and keep going with the research. But yeah, we need to ask permit to get samples, but not. I remember in Australia, it's quite strict. You need to do your request really at an advanced time. Sometimes you don't have it. Sometimes you start your field work and you still don't have the permit. So yeah, it's not the same.
No, it's interesting because I'll come on to a couple of questions in a minute about management opportunities, but that kind of was why I was wanting to know. So I guess a question that I had was about the species. So like Acropora tenuis, there's obviously been a bit of a recent revision in that taxa. And like my understanding is that we don't have tenuis actually on the Great Barrier Reef anymore. There is tenuis in other areas. And do you know if you actually have tenuis or if it's kind of something closely related? And I guess a follow-on from that is a comment just that I totally agree with Sylvain that the population genetics of those sites will be really fascinating to look at.
That's a really good question. And yeah, I think there is a paper that's called That's Not Acropora tenuis that being published for Australia because, yeah, you know, the problem with this type of study, so we are discovering new species. We know that the colonies in Boracay and the nearby control site are 100% Acropora tenuis because there are previous genetic analysis that was made by Gregory Torda. So we know for sure that those are Acropora tenuis. In the reference site, Prony, we actually didn't do any genetic analysis, but they look really similar, which gives you a little bit of space for like a mistake. But we know that we have Acropora tenuis in New Caledonia, and so I'm pretty confident that that's Acropora tenuis.
No, it's interesting because when you look at that paper, there's like New Caledonia is in the middle of like where they've said it is and it isn't. And so that's why I was interested to see if you had any confirmation, because when you look at the Tom Bridges paper, like where New Caledonia is, there isn't like data from there. So that's really cool. So thank you, Cinzia. So a question I had about obviously the Symbiodiniaceae aspects of your work. So I think often we think of kind of resistance and resilience, that diversity is really important, and having diversity often feeds into that, at least at a reef scale. But it's interesting that then when you look at the symbiont communities, you get less diversity between individuals in the symbiont communities. And I guess I wanted to see what you thought about that, and if you think it's, you know, maybe part of the survival, or is it potentially a risk that there isn't as much variation in symbionts in Boracay?
Yes, thank you for the question. It's really an interesting question. Yeah, I think that could be a bit of risk because there is a decrease in diversity. That was actually scaring when, no, it's not scaring, but it was impacting when I saw the results, because really if you compare, and actually if we have like the results, which are really from Acropora tenuis, going back to Acropora tenuis, from the offshore side, inshore side, and Boracay, you actually can see that there is a really big difference in diversity between and kind of gradient. So we know that Boracay is affected by high fluctuation and low extreme environment condition. R2, it's a bit in the middle without variation, so there is already a decrease in diversity, and Prony, it's really, there are different species. At the beginning, when I saw that, that was the first time I analyzed the data from Acropora muricata from the second point of this chapter. I thought that maybe there was at the base, it could have been explained by the bleaching adaptive hypothesis, where colonies can bleach and that they will uptake symbionts from the surrounding environment that resist to stressful condition, and that could be used as a strategy to better handle future stress. That I thought that because I observed the bleached colonies that actually change their major sequences after bleaching. So they probably, then I start asking to myself, okay, they changed their major sequence because they decide to change it. I mean, they kind of did a selection, or because they were forced to do that. And then more I thought about it, more I start thinking that's really environmental selection, also at the Symbiodiniaceae community in local place. I can't confirm that because we don't have data on the environmental conditions, so I don't know the free population in Boracay, if it's really this change over time after big stress or not. So I can't conclude on that, but I think that decrease in diversity, like between individuals, it's actually it's not good. because it will bring to decrease in diversity. Therefore, if we have a really type of stress where these symbiodinaceae are not prepared, so then maybe it can be a strike for the population as well.
Yeah, that was a really good answer. And I think it kind of went also my thoughts to something Sylvain mentioned, which was about the different types of stress, because I found it interesting that you didn't see the shift with the transplantation as much, but then obviously when you had bleaching, you did see that change in community. And again, I think that differentiation between types of stress is something that kind of was a theme that came out of your thesis, at least when I was reading it. So that was just a comment. So I guess just to kind of wrap up, because I think my other questions you've already answered. You know, we talk about these systems. I've talked about them as their potential value in restoration, and obviously the more that we look at them, we see that there are trade-offs, and your thesis has shown really species-specific responses. So I'm keen to get your thoughts on what the value are beyond obviously being natural laboratories of these sorts of systems and the corals that live there.
Well, I think this type of system are really important because provide really ecological relevant information. Yeah, I think it's what we observe in the system is actually what we could observe in the future, maybe not at the same in the same way, but it actually tell us a lot. Like, for example, 2 years La Nina in a row, we observe a decrease in species inside Buraque. We know that with climate change, we will observe an increase in frequency, intensity of those type of events. So they might affect coral population. And from this natural analog and natural laboratory, we can see what are the species that can thrive better in those conditions rather than other species. Of course, we can't, I mean, there are a particular system, there are a lot of stress going on. It's like, we can't apply the results we observe in Buraque everywhere, but it's actually providing information. Like, for example, the decrease in diversity between individual and algal salmon community is already important information, because tell us what type of symbiodinaceae can survive under stressful conditions as well. So if you want to do some cyst evolution, for example, you know what kind of symbiodinaceae you can look at. So there are different type of information you can get from this system that are really important. So yes, I think those are exceptional sites. I don't think you can get the same results working in laboratory conditions in a lab. So yeah.
Thank you.
And congratulations again on the great thesis. That's done. Thanks.
Thank you.
Thank you, Emma. So, Tom, it's your time.
Okay, so thank you, everybody, and mostly thanks to you, Cinzia. So I don't have all that many questions left. So first of all, I'll pass some of my time in congratulating you. You gave a great talk, great presentation. I enjoyed reading through your thesis. You made a lot of work on a wide-ranging, like so many different topics. You really tackled it from many different angles. You have a very interesting study system over there. And together with the unique events, La Nina and everything, I think you really made the most of it. It's really impressive, the amount of work. It was said before that you spend a lot of time in the field and diving, but I suspect you might have spent more time in the lab, actually. And I applaud you for all those efforts, like really impressive. So really, just my esteemed colleagues before me went along. I just took off every question I have one after another, so I'll try to come up with some new ones now. So continuing with the line of Emma's last question, so I think a lot of the incentive and motivation we have in recent years to study those unique extreme environments, right, is because we see that corals and coral reefs all over are just dying fast, and then we are surprised to discover that under such harsh conditions, suddenly corals can survive. And maybe it could teach us something really, like you said, about how can they survive in future ocean or potentially expand from those unique locations to other nearby reefs that degraded, right? So I wonder, considering some of the results you showed, what do you think that, if the coral reefs outside of Boracay now all bleach and die tremendously, what are the chances that corals from those semi-enclosed lagoon or similar areas can expand outwards? Can they replenish nearby degraded reef? What do you think?
Can you repeat the second part of the question? Sorry.
Yeah. So I'm asking, what do you think is the probability that corals from such a unique environment, like you showed us, and the unique acclimatization or adaptation they go through, so what is the probability that corals from inside this lagoon will manage to settle outside and live there and prosper?
Yes, I think that the colonies inside Boracay have higher probability of survival of other colonies that are outside than what I saw basically with my experiment with the offshore colonies, because they are exposed to different type of environments. What I will think that probably this population could serve as like gametes sources or larvae sources to settle in a new environment. Of course, they can't keep all the surrounding reef alive if there is a massive bleaching. But yeah, I think they will have, they are quite resilient and they have higher limits compared to the other corals, if I reply to your question.
Yeah, kind of. So let's develop this conversation a bit further, if you don't mind. So you find some nice mechanisms of acclimatization. For example, if I remember correctly, the Symbiondinium types inside Boracay and also a bit in the inshore reef were quite unique, specific. Generally, the Symbiondinium community was less diverse inside Boracay, right? At least in Acropora muricata.
Yep.
And like there was a different community there. So perhaps it's a more specialized community of symbionts to the unique extreme conditions inside the lagoon. And perhaps this association of host and symbiont will not be so successful outside. I mean, it fits the environment. Doesn't necessarily means it's better everywhere, right?
Yeah, definitely agree. Yes.
So my question about that would be, how would you test it? What would you do today to check this kind of
how do I test it? Well, the experiment you could do just on the symbiont. So just to clarify, the symbiont that we found, the symbiont species, algal symbiont species, what we found inside Boracay, that was really specific. It's mostly belonging to the sequence C1. So it's as a species, it's Cladocopium proliferum. And there are a few studies already in Australia that tested the stress tolerance of this this algal symbiont species in specific, and they observed that this species is really it's really plastic, which means if you expose this species to different type of stress, they can increase their tolerance compared to other species. So I think it's true that if you observe the same algal symbiont species in different environment, that doesn't mean that this type of species apport stress resistance. That's because, as well as what I observed with my results, because in Boracay and inside shore site, For example, in Acropora was the same species, but the colonies respond completely differently. So in my opinion, like the Symbioninaceae of this species of symbiont that was inside Buraque was actually exposed to stress and increased its tolerance over time. So it's not just linked to the species, but it's more linked to exposure stress.
Yeah, I guess. So if you tested, like you took some corals from control sites and transplanted them inside the lagoon, I guess I'm saying you could do just the same and taking some fragments from the lagoon outside to the control reefs, right? And make a reciprocal translocation and see also how those react and respond in different environments. I think that could give also some clue about how these corals can, at least adult, can tolerate other conditions.
Yeah, that's kind of information that's missing in my thesis, but yes, will be.
Yeah. We can always, criticize somebody for doing more. It's easy to sit here and tell you why. Yeah, no worries. I'm just thinking that, for corals that probably inside the lagoon, the water is also murky, right? We saw the light measurements, the light levels are low. So exposing them suddenly to a control reef with high amount of light and intensity can be a stressful event for those who are adapted to different conditions.
Yeah, definitely.
Yeah, cool. Thanks for your answer. I appreciate it. You also mentioned that in some of your translocations, you measure the changes or increases mostly, if I remember right, in the symbiont density and chlorophyll, right? And you mentioned that it's probably because of nitrogen availability, either from nutritional plasticity or microbial activity. And again, I think there might be some more environmental factors that influence the density of symbionts and pigments, right?
Yeah, I think the environment can also influence that because yeah, it's a mangrove, so there is a lot of organic matter that's produced. And this organic matter, we know that corals that are fed, for example, they increase their chlorophyll, they increase their symbiont density, they increase their calcification. So of course, this type, and other things that I think should be done in the future. I didn't put it in the perspective because I think there are so many things that could be done in Buraque that it's a huge list. But that's definitely, I think, it's something that should be tested because what I observed during these 3 years, for example, it's like the corals that sometimes get covered by it looks like a sediment, but it actually comes from the mangroves, is organic matter. So they are forced to remove that type of organic matter, particulate organic matter from themselves. So I guess they ingest it and they expulse part of it. So I think there is a kind of forced nutritional like heterotrophy goes on, but it's not clear how. So I think it's something that should be really tested. And yeah, that could explain the increase in zooxanthellae and chlorophyll, definitely.
Okay, thank you. And now I want to move on to the most interesting topic of all, reproduction and spawning. Yeah, so let's just have a couple of questions and that's it. So first of all, I saw you had nice, cool photos of the spawning events itself. So I take it that you went and observed some of those events, right?
Yes, definitely. Yes, there was actually another objective in this case that got removed that was testing the physiology of the larvae. So we performed the spawning in controlled condition, and we also observed the spawning in natural conditions. So yes, the answer is yes.
I see, because it wasn't mentioned in the thesis, and I was curious trying to find out when and where did you observe the spawning, and how many nights you checked, and what did you see?
Yeah, so this part is not in the thesis because we couldn't conclude a lot on that part, but we did the spawning control condition in the 2020, 2021, and 2022. No, 2021. We canceled in 2022. So yes, the first time we just brought some colonies at the Aquarium de Lagoon here in Numea. So there was in a controlled condition at the aquarium. It was quite not easy because it's always a spawning. So there's a lot of stress. It's hectic. I think you know exactly how it works. But we managed to do the fertilization. We got some larvae from Acropora tennis and Montipora agitata. We settled them on plugs and actually transplant few of those plugs in the field. But we didn't get the recruits from both population. We just got, I think it was Acropora tennis from Buraque and Montipora stellata from the control. I don't remember exactly now. I should look at my notes. Then the same year, 2020, we're trying to do it in the field. So there was a bit of difficulty, higher difficulty. So we took the colonies from Buraque, a nearby control site. We put them in the back and we observed the spawning behavior. And we did that starting from the first day of full moon until the 5th or the 6th day. We stopped at a certain point because most of the colony, some colony spawn. And that's when we observed that especially Acropora colonies, Acropora tenuis, spawn in October rather than November. So there I start to raise some questions, while Montipora spawn in November. So yeah. Then I did also other observation the year after, and but that was a bit different. So because we changed the place where we did the spawning, there was at the Ifremer station. So we observed again the spawning behavior and everything, but in that case we couldn't manage to get some larvae from Montipora from the control. That actually I settled in, I used the larvae because we didn't do any experiments, so I settled them in the natural, original site. And I followed a few individuals over time just for curiosity, but we didn't conclude any results on that.
I see. Well, thank you, because I totally agree with you that there's almost no information on reproduction in New Caledonia, and it's surprising considering what the system you have there. So I have to say, I really like this chapter in your thesis. I just had a bit of an issue with the title. So you say, you titled it as spawning, timing, and fecundity are not affected by extreme environmental conditions. And I understand the desire to give such a statement. But then most of this chapter, and hopefully soon to be paper, right, is dealing with the differences you found. So perhaps not in fecundity per polyp, but you do mention differences in fecundity per colony, whatever that would mean, and in the spawning estimated periodicities, I also think that your results are much more nuanced than just saying these are synchronized or not. And I wanted to ask you in this regard, what does synchrony, what are we talking exactly? Because sometimes we confuse these terms, me as well, yeah?
Yeah.
So you mentioned synchrony between different locations, so potentially different populations. And I think you made a nice discussion about the potential connectivity or lack of potential connectivity, which we need some population genetic studies. And then it's also, it feels to me it's a bit getting mixed, the synchrony between the species or the synchrony within population.
So yeah, thank you for this actually comment, because, sorry, I cut you. I didn't mean.
No, go on, please.
It's actually a really good comment, because when you talk about synchrony, it can be, especially in reproduction of corals, it can be synchrony like same time, it can be same month of spawning, it can be synchrony between species, it can be intra-colony synchrony. So I think like there's already high variety of the use of this term in reproductive of corals, reproduction of corals. So what we meant with that statement in the title, it's because I personally was expecting an effect of the variable condition on the spawning window of those corals. I was expecting the Burakia corals would have spawned before than others. So at the beginning, during the first year especially, I was also taking the time of the spawning and all those metrics. So I realized that maybe, as you said, when we talk about synchrony, that's why we call it spawning window, because it's like synchrony, it's really maybe related more at the moment when colonies spawn, so timing at their spawning time, rather than period of the month. So we didn't observe, that's why the title is a bit like that, because we really observe similar pattern in the spawning month between northern and southern region.
Yeah. So I'm just saying, I think there's much more to your results than the way it's now being communicated. You worked on several reproductive traits in several sites, and you did find all kinds of differences that relates to the different sites. And I think personally, it made me very curious about a lot of things that's going on there. Worth diving into that a bit further, to my opinion. Last question about that, because I imagine my time is out. So you mentioned you sampled these corals to measure the reproductive traits at October, November, and December. And now you showed us just the results of October and November and estimates of spawning, not spawning, which I'm not entirely sure what it meant, spawning, not spawning, sorry. But I wonder what happens in December. All colonies are just empty, nothing left anymore, or there's something still fertile?
That's really good question. So I talk about estimated colony, estimated to spawn, just because I didn't observe the spawning with my eyes. I calculated spawning time, spawning window, spawning period, I don't know how to say, with the fecundity data. So I look at my fecundity data, and then I collect some samples like October, November, and after the spawning on November, which was at the beginning of December. So I didn't wait for the spawning of December. That's why I talk about estimation. Then I went back calculating the data, and I realized it was not easy because, you can have intra-colony spawning as well, for example. So since it was a bit complicated, we settled some kind of rules, and I hope that you can tell me that we made it clear in the paper. So we define, we characterize colony level fecundity for those colonies that had the number of polyps that were empty in the fecund branches. And then we define if some colonies spawn in the meanwhile between 1 month and the other with the 2 branches that were completely empty. Then if there was 1 branch that was empty and 1 branch that was full, that was calculated as intra-colony spawning. But we didn't have that many cases. I think there was just 1 colony of Montipora in the southern side. So we just took some decision and we applied them. But I know it's not easy, because actually, it's not easy.
Okay. Great. Thank you for your answers. These were really, again, beautiful talk, beautiful PhD, great answers, and congratulations. I'm done.
Thank you so much. Thanks.
Thank you, Tom. Now, Ricardo, are you ready?
I don't know. Allez, Cinzia, terminé. Well, I have 15 questions for you.
Vas-y.
I will just tell you 15 and then you will resume in one answer only.
Yes, if you want.
I have no more to add, honestly, to what you say and what they ask this reviewer reporter. We talked, discussed, argumented during the last 3 years, 4 months, 2 days, 7 hours. So I think it's enough. I just want to say that my congratulations for all the job you have done. We have selected, this is for the people, we have selected Cinzia because we wanted someone independent, and we choose well, honestly. Today I would like to thank you these 4 experts we invited. We have been lucky to have all the comments that honestly helped even today to better understand some results. And we have been, I can say we have been in difficult. We are 3 people here that supervise this PhD that is huge, and some more results are still on the desk. So if in the future I had a new Cinzia in my lab, I think I will ask you to supervise with us, because it could be much more easy and maybe we could understand more than we have had until now. So really, I have no more question. I really thank you. I thank you, Cinzia. Cinzia has a job ready in Palau, so that's great. That shows that she's ready to make research. This is what I hope for her, and what we could do, we did. That's enough. Thank you, Cinzia.
Thanks.
What can I say? Dear Cinzia, I am glad to be here, honestly. I am happy to see you on this stage. Really happy for that. And in your thesis, I have learned a lot about the world of coral reef. I did not know nothing at the beginning of your PhD, it's honest. And now, and with your help, I know now that I don't know. And I think it's the first step for me for the knowledge. And as consequence of your work, and with the help of Ricardo, your PhD has opened doors for me. Now I can ask myself questions and identify some scientific issues in my own field, the coastal environment. And particularly on the Boracay site, where we have begun another PhD work. Many thanks to you for that. A big thank you to Ricardo for integrating me into your Italian team. After my Corsican, Caledonian, and Indonesian periods, I can call the last 3 days my Italian period. This last experience proved me that I am able to acclimatize myself to human socio-ecosystem characterized by high temperature and sometimes low oxygen pressure. But Italian food is really good. Even though I have lost weight recently. But eating well is the key for acclimatization, you know that, and will be the subject of our next work with Ricardo and Fanny. Cinzia, more seriously, you have to adapt yourself to the French research. Now you speak our language. Tu parles français. Très bien. You have finished this thesis. Well done. I can say just that. Well done. I wish you all the best, and I hope you find what you are looking for in Palau. Trust yourself. It's really important. And don't forget us. Some part of your work have to be published, please.
Thank you.
Okay, so Cinzia, here we are. And thank you for your very nice presentation and the very interesting exchange with the member of the jury. It was really enjoyable for me. As you know, I am not specialist of corals, so I learned a lot of, like you say just previously. I would add also to express my personal satisfaction at this achievement and add my congratulations to those of the examiner and rapporteur of this thesis. You have done a very, very nice job, and well, I think we are all here very proud of that. I would like to thank the members of the jury for their investment in the analysis of your manuscript and the very, very interesting discussion which served to highlight your mastery of the subject. And I was very, very impressed that how you can answer the question, and well, this is a trait of your character. I would like also to express my gratitude to Ricardo and Hugues for their scientific guidance throughout all these 3 years. And I am very pleased that Ricardo found some time to have the total legitimacy to sit here as the main supervisor of your thesis. So for you, having 3 supervisors was not very easy for you, but it was, I think, necessary to channel your overflowing enthusiasm. This was one of my main jobs, to stop you and your enthusiasm, and you want always to do more and more. And as Ricardo and you say, you are very, very hard worker in the lab, in the field, and part of our energy has been to restrain you desire to do more and more. So in the meantime, you learn French, and I don't know if the member of the jury know that, but I'm sure that you can take the floor in French and you take it in English. So you learn with the choral, the French, the English, and this is very, very nice, and I congratulate you for this effort. Your work is bringing important results in the understanding of the functioning of the corals in Boracay, and in this sense, you have honored your contract, because when you start, you have to attain the objective, and you do that, and I have to say thank you for that, because there is some engagement for the financial support. Having said that, you have accumulated a lot of and a great amount of original data on coral metabolisms that deserve to be analyzed in more detail, with the aim of proposing indices, for example, for the health of the corals. And you know that you have little effort to do to go deeper in the analysis of this amount of data. So I know that you are jumping very soon in a job in Palau, at the Marit session, I think in Palau. So I hope you will be able to devote some time to finish the analysis of this work, because I think it's important for you to publish these very nice results. And it's important for the coral community to have this data on hand. So I will really encourage you to do that. And I will finish by saying that I have enjoyed following your work, and I have learned a lot on the corals. And as I say at the beginning, before you start, you are the last student I have pleasure to supervise, because you know that I will leave the professional activities by the end of this year. So I am very proud of that. I wish you all the best and hope that you will have the opportunity to read. You will have the opportunity to read your future scientific papers. Once again, all my congratulations and many thanks to the University of New Caledonia and its staff for providing us a warm welcome in the campus. So thank you again, Cinzia, and good luck for the future.
Thank you, Claude.
Here we are. So thank you, Cinzia, for your presentation. It was very clear. All the results, all the discussion was in English, and it was said by Claude and the other. It's not your native language, so well done for that too. I've been following the progress of your work during the comité de suivi individuel, which is such a kind of annual reporting on something like that. And I'm really happy to see its final step today. So we are close to the end of our discussion. It's time for a drink, something like that. And I just have some technical comment or a few questions. The most important points were already discussed, so that's good. Just a small question regarding the control site. They were all relatively distant from Boracay, so why didn't you try to sample on the barrier reef close to Boracay? Could be interesting too. So could you explain in a few words?
Yeah, I think that it was even more interesting getting Tania, for example, like just in front of Boracay, maybe do a gradient of sites. So Boracay, the middle sites, offshore, inshore site close to Boracay and offshore site just in front. But logistically was not really feasible. So at the end, we just decided to keep some offshore site here in the south, Recife de Brony, just for logistic.
Okay. Why not? I can understand that. Another question is just regarding that slide as an example, because I'm not familiar with such results. So does it mean that you can consider you have different species, you have different clades or something other within this type of results?
Yeah, so these are the major sequences, which sometimes it doesn't really mean that you have the same exactly species, because you can have some variation. So maybe sometimes you can have, for example, C1b, it's probably C1. So that's why there are just sequence, but the major one can be seen as a species. But then if you start to distinguish between the less represented sequences, then maybe you can have the same species between the major and the less represented, okay. Because just there are portion of sequences, so sometimes you can sequence them, but you can
okay, thank you. Just another small question, or maybe a remark. As it was said by Christine at the beginning, you are speaking about protein, lipid, and so on. They are compounds, of course, but it's also energy. Okay, so it could be interesting for maybe your next thesis next year to look at the energetic values. So maybe to look at how energy is used for calcification, how it is used for other process. So it could be interesting to look at such a kind of data in the future.
Yeah,
so
I agree.
Your next thesis, maybe. Okay. That's all for me. I just want to know what will be your work in Palau.
I'm gonna work as a research aquarist at the Palau International Coral Reef Center. I'm gonna just be involved in a Corda project that's about assisted evolution of corals. So we're gonna propagate corals from known parents, known generation. We're gonna to develop the third generation, I think, of one species, and we start with other species. So we look at some traits. I'm gonna just provide technical assistance and all of this. The project is not running by me, but gives me the opportunity to learn a lot. So then we're gonna start with one generation of Goniastria. So a new species, and yeah, I will have the freedom to also develop. That's what they say. That we'll see when I start, but they say that I also have the freedom to develop my own research interest. So there is a kind of 1/3 of my time I can dedicate it to that. So it looks like really a nice opportunity, and I will work with James Guest and Adriana Humanes, which are really known in the field, and they are really good specialists in coral reproduction, which is what drives my passion right now. So yeah, that's it.
Okay, thank you. Nice work. It looks nice. Okay, that's all for me. So we now will deliberate.